Hello there, Mr. Sutton here with the AB Calculus 5.9 homework solutions on FTC graphical analysis. On this problem, we've given this graph of f here and also this g function that's essentially the integral of f from -2 to whatever, and we're trying to figure out which of these values of g is going to be the greatest. One way you could do this is just plug all these numbers into this function, but that could take a while. So we're essentially trying to maximize the g function over the interval from -3 to 2. Another way to do that is with the candidates test, where you basically test out the endpoints and critical values in this function, and you know the max is going to be one of those. Another way to do this, and you're going to still need the derivative for this, and the derivative of g is just f of x here. Another way to do this is to say, okay, f, or g prime, is positive, greater than 0, on the interval from -3 to 1. So that means the g function is increasing this whole time because its derivative, which is graphed here, is positive. And g prime, or f, is less than 0 from 1 to 2 for the rest of this interval. So that means the g function is only decreasing after it gets to x equals 1. Well, if it's increasing before 1 and decreasing after, that means that x equals 1 has to give you the maximum possible value of g on this. Because if there were a higher value, you wouldn't have been increasing to get to 1. So that means that it's going to be answer choice D. On this problem, we're given this piecewise graph, and h is defined as the integral of this graph from -1 to whatever you want to plug in. So we want to know on which of the following intervals is h increasing. Now be careful here. They're asking where h is increasing, not f. But there is a relationship between h and f. If you take the derivative of both sides of this equation they gave us, we see that h prime is none other than f of x. So that means they're giving you a graph of the derivative of h. And we see that the derivative of h, f, is positive from 3 to 9. Well, that means that h itself must be increasing on the interval from 3 to 9. So that gives us answer choice E. And don't be discouraged by the brackets there. We know with increasing, decreasing, if things are continuous, we're allowed to include the endpoints in the interval. On this problem, we've got this differentiable function f in the graph, and h is defined as the integral of f. So we want to know what's the correct order of h of 2, h prime of 2, and h double prime of 2. Now, the key to all of this is this f function here. Because we don't really know a whole lot about h other than how it's related to f. So the key here is that if you take the derivative of both sides, h prime is f of x. F is the derivative of h. So now going through all of these, let's just figure out what they are. H of 2, that's just the area under the f function, the area under this curve here. And it's the area from 0 to 2 in this case. So this area we don't know exactly what it is, but we do know that it's positive. So I'm just going to write greater than 0 there. Now for the next thing, h prime of 2, that is just basically f of 2. F of 2 we can just look up in the graph. That's the y value where x equals 2, and that's right here, that's 0. And then finally, h double prime of 2, that's asking for basically f prime of 2, or the slope of this f graph. And at 2, we see that the f graph is decreasing, so that slope is negative. We don't know exactly what it is, but we know that it's less than 0. This information by itself is actually enough to put these in order. So the smallest one is going to be the one that's less than 0. That's h double prime of 2. The next biggest one is going to be the one that equals 0. That's the h prime here. And then finally, the biggest one is going to be the positive one, h of 2. So that gives us, let's see, h double prime, h prime, and h. That's going to be answer choice E. For this problem, the graph of the derivative of f is shown in this figure up here. We want to know which of the following could be the graph of the original function f. So looking at our derivative, there's a few key features we're looking for. I noticed that we have the graph of f prime crossing the x-axis at -2 and +2. So that means that we're going to have some kind of smooth turnaround for f at those x values. So let's look for smooth turnarounds down here at negative and +2. Well, that rules out choice A and choice B. Those are all straight lines. Choice E is an option because we've got these smooth turnarounds here. Choice C, not quite. The smooth turnarounds don't happen at negative and positive 2. Choice D, though, is still in the running. We also have smooth turnarounds there. So really what it boils down to is where are things increasing and decreasing for these graphs, because everything else is pretty much the same. So taking a look then, we see that this graph, f prime, is positive, greater than 0, on the interval from negative 2 to 2. There's other observations I could make, but let's just go with that one. So that means that the graph of f must be increasing from negative 2 to 2. So between our choices, D and E, only E is increasing between negative 2 and 2. So that has to be choice E then. For this problem, we're told that the f function is the integral of the h function, and h is actually shown in the graph up here. So we want to know which of the following is the graph of f. So the key on this one is recognizing if you take the derivative of both sides here, that f prime is really just h. So this h graph here, you can think of this as just f prime. This is the derivative of something down here. So with that in mind, let's see if we can pick out the graph. One thing I notice, I always look for x-intercepts to start off here. I notice that the graph of h, or f prime, crosses the x-axis at x equals b. So that means that the graph of f, somewhere down here, must have a smooth turnaround, some kind of local extremum at either at x equals b, either a smooth max or a smooth min. So taking a look at b, that narrows it down a little bit. Choice A can't be it, because this is not a smooth turnaround. It's a turnaround, but this is a cusp, so that would have caused the derivative to be undefined. Choice B, same issue. We've got a cusp there, not a smooth turnaround. For choice C, we don't have any kind of smooth turnaround at all. And choice D, that might be a smooth turnaround. It doesn't quite look like it lines up, but maybe. So D, I'm not going to throw out just yet. Maybe it's just a little bit weird the way they drew it. Choice E definitely has a smooth turnaround at B. So really we're down at this point to D and E, probably E, because D looks a little off, but let's keep going here. Now, one other thing we can tell, the smooth turnaround in choice D is a min. The smooth turnaround in choice E is a max. So let's look at our derivative and see if we can figure out which one that smooth turnaround ought to be. We notice that f prime, or h, goes from positive to negative at x equals b. So that means that we must have a max on the graph of f. So that then confirms that answer choice E is what we're looking for. For this one, we're given this crazy looking graph of f, and g is defined as the integral of f from 0 to whatever. We want to know, based off of that, the value of g of 5. So for this one, all you really have to do is plug 5 in here and find the area under the f curve from 0 to 5. So here's what we're essentially doing, integral from 0 to 5 of f of t, or f of x. And for this one, so we've got a few shapes here to find the area of. We've got this triangle, and that means that we're going to have, let's see, that's going to be 1/2 1 times 3 for that area. Next, we have this semicircle. So for semicircles, we have 1/2 times pi r squared. R in this case is 2, because from 3 to 5 is the radius. So we're going to have 1/2 times pi times 2 squared. And is there anything else? Nope, that's it, all the way from 0 to 5. So adding this up here, this is going to be 3 over 2, or 1.5, because it looks like they've got some decimals in the answer choices. And this next one, half of 4 is just 2, so this is 1.5 plus 2 pi, which gives us answer choice D. For this problem, big F is some function defined such that f prime is greater than 0 and f double prime is greater than 0. Based off of that, which of the following could be a table of values for f? So we have to just kind of translate what this means in words here. If f prime is greater than 0, that means the f function is increasing for all real numbers. And if f double prime is greater than 0, that means that f is concave up for all real numbers. So if you're increasing and you're concave up, that means that you're increasing at an increasing rate, like this, like the right side of a smiley face. So we have to look for the table that has values increasing at an increasing rate. Let's go through them all now. For choice A, we're going -3 to -4 to -6. So this is actually decreasing. That's definitely not a good answer choice. Choice B, we're going -3 to -1, so that's increasing, and then 3 and then 19. So we appear to be increasing, and the rate of increase is also increasing. So B is looking like a pretty good answer at this point, but let's just look at the other ones for the sake of argument. Choice C, -3 to 0 to 3 to 6. So this one's increasing also, but it just keeps going up by 3, so a constant rate of increase, which does not match the concave up character of F. For D, we're going -3 to 5 to 11 to 13. So this is increasing, but it's increasing at a decreasing rate. We're going up by 8, then 4, then 2. So this one also is not concave up. Choice E, we're going -3 to 4, and then back to -3. So this one is not even consistently increasing. It's decreasing and increasing. So that doesn't even match the first trait there. So out of all of these then, choice B, increasing at an increasing rate, is the way to go. For this problem, we've got the graph of the f function here, and we want to know the relationship between the integrals of f from 0 to 2, 0 to 3, and 2 to 3. So basically, we're just being asked to compare areas under this f curve. So let's just look at all of these. From 0 to 2, that's this area right here. And we don't really know how much it is, but we can say it's definitely all positive area at least. So that's something. Now the area from 0 to 3, in contrast, is both positive and negative area, so that's a mix. And then the area from 2 to 3, well, that's all negative area. So although we don't know any specific numbers, we do have enough information to at least put these in order. So these go from smallest to biggest. We know that out of these three situations, the smallest is going to have to be the one that's all negative, especially because this negative and this negative are the same thing. If we don't have any positive to balance out the negative, this has to be the smallest. So it goes integral from 2 to 3, and then the next biggest is going to have to be the mix of positive and negative. And then finally, the biggest one is going to have to be the one that's all positive and didn't have any negativity dragging it down, so integral from 0 to 2. Looking at our answer choices, that appears to be choice D. For number 9, we've got this piecewise function that we're looking at, and we're given that g of x equals the integral from -3 to x of f of t dt. And this is actually the graph of f up here. So we want to figure out g of 0 and g prime of 0. So 2 for the price of 1 on this thing. Let's start with g of 0. That's just going to be the integral from -3 to 0 of f of t. So here we're talking about the area under the f function. If we go from -3 to 0, this is just a trapezoid here. So using just some basic geometry, we've got base 1, which is the 2 here, plus base 2, that's the 1 over here, always divided by 2, multiplied by this sideways height of 3. So basically just your normal trapezoid kind of formula. And for free response, we're going to leave it like this. If you really have to simplify it, if you want to live on the edge, you can call this 9 over 2, but there's really no benefit to doing so on the AP exam. All right, moving forward now with g prime of 0. So since g is this integral with an x in the upper limit, taking the derivative of this using our fundamental theorem of calculus, we're essentially just replacing t with x, multiplied by whatever the derivative of x is, but that's just 1, so that doesn't matter. So g prime of x then is just f of x, which means g prime of 0 is just f of 0. What is f of 0? That's the value of the graph of f at x equals 0. So here's x equals 0. Going up, we see that we have an output of 1. So there we are. For this problem, we're being asked to find all values of x from -5 to 4, where the g function hits a relative max, and then justify the answer. So if we want to know the relative max for g, we need to know the derivative of g. Now looking back at this equation they gave us, they said g was the integral of f. That means that g prime is going to be just f of x, because using our fundamental theorem, we're just plugging in this variable in the upper limit for the dummy variable in here. So we've got g prime is f of x, which means that if I want to know what g prime is doing, well, I've got a graph of g prime up here. It's the same as the f function. Okay, so we notice that f, or g prime, goes from positive to negative at x equals 3. that means that the g function itself must have a relative max at x equals 3. On this part of the problem, we're trying to find the absolute minimum value for g on the closed interval from -5 to 4. So for this one, we need to either do the candidates test or some other kind of test. Either way, we need to remember that g prime equals f. That's the key to any technique we're going to use. Now, in terms of picking a technique, if there were only one x-intercept for our derivative graph here for f or g prime, then we could just talk about the sign of f before and after that critical value. Since we're crossing in multiple places, we're going to need to use the candidates test. Now, the candidates test basically says you're taking the endpoints and any critical values in between and plugging them all into this function and then just picking in this case, the lowest value for absolute min. Now, the good news is we actually, for the interior critical values, we only have to consider places that are local mins. Because if something's not at least the lowest spot in its immediate area, there's no way it's going to be the lowest spot for the entire graph. So we only cross our f graph, our g prime only crosses from negative to positive at x equals -4. So we just have to test -4 and the endpoints -5 and 4. Okay, so now that we saved ourselves 2 critical values to test, let's start testing. G of 5, that's going to be integrating backwards from -3 to -5. So we're just doing area under the curve. We have some positive triangle area here, but since we're going backwards, we have to subtract this triangle. So that's going to be minus 1/2 times 1 times 2. And then we have to also do this negative triangle, but again, since we're going backwards, that's going to be a positive because we're subtracting a negative area. So that ends up being plus 1/2 times 1 times 2. And these are exactly the same thing, so they just cancel and give us 0. Moving on to -4, that's not too much worse to test. -4 is just subtracting this positive triangle here, so -1/2 times 1 times 2. It's just the first part of our expression for g of -5. So this ends up, if we simplify, it ends up giving us -1. Now, the next one's a little bit of a doozy. We just have to test 4, but 4 is all the way over here with a whole bunch of shapes and geometry in between. So let's go from left to right here. So we're going to have this trapezoid to deal with first. That's going to be the bases of 2 plus 1 divided by 2 times 3, height of 3 here. So that's giving us this trapezoidal area. Next, we have to deal with this semicircle, but it's not really a semicircle. It's the area under the semicircle. To get that, we're going to have to actually take a rectangle and subtract this semicircle out to get the remaining area. So the rectangle is just going to be 2 times 1 for that area, but now we're going to have to subtract the actual semicircle. So we're doing minus and then pi times the radius of 1 squared, and 1/2 actually times that. And then we have these 2 triangles. We're adding this positive triangle, so plus 1/2 times 1 times 1. But then we're subtracting the exact same dimensions of a triangle. And now we have to figure out what all this comes out to. Normally you don't have to simplify your answers on a free response, but if you have to compare your answers to see who's the smallest, well then you kind of need to know what you're looking at. So let's see here. We've got, this is going to be 3 over 2 times 3, that's 9 over 2. Plus 2, well, that gives us a common denominator of 2, so that's actually 13 over 2. And then as we move here, this is going to be essentially pi over 2. So we have 13 over 2 minus pi over 2, and then these 2 expressions just cancel. So this is what all of that comes out to. Now, how does this compare to the other things? Well, pi over 2, pi itself is just a little bit more than 3, so this is like about 1.5 and some change. 13 over 2, well, that's 6.5. So this definitely comes out to a positive number, at the very least, whatever it is. So that means there's no way this is the absolute min. So between the others, -1 is the lowest. So by the candidates test, then, -1 is the absolute min for the g function. On this one, we're trying to find all values between -5 and 4 where g has a point of inflection. So again, keep in mind that g prime equals f, or f equals g prime. So we're basically going to use the graph of f here to tell us what's going on with the g function. Now, we know that points of inflection are going to happen wherever g prime goes from increasing to decreasing or decreasing to increasing. That's the same as having a sign change in g double prime. But I'm not going to bother talking about g double prime because we haven't defined it anywhere. It's f prime, but then you're going to have to talk about how f prime is changing. And that would require a little bit more work. It's much easier just to talk about where the f function is increasing or decreasing. So we notice that the f function is going from increasing to decreasing at 2 spots, here at -3 and here at +2. And we also notice that the f function, or the g prime function, is going from decreasing to increasing here at x equals 1. Therefore, because we're changing direction at these spots, that means the g function has points of inflection at -3, 1, and 2. For number 10, we have a continuous function f defined on the interval -4 to 3, and the graph of f given here has 2 quarter circles and 1 line segment. And they're also telling us that some other function g equals 2x plus the integral of f from 0 to x. Based on that, we want to find g of -3, g prime of x, and g prime of -3. So there's 3 different parts that our answer needs to have. Let's start with g of -3. So for this one, they already gave you what g is doing. We're just plugging -3 in for all the x's, like so. So in order to calculate this, you do need to figure out some numerical value for this integral before you can get any credit. So we've got -6 if you want to simplify that, although it's not necessary. For this one, we're talking about the area under f between 0 and -3. And we have to be careful because we're integrating backwards to do this. So this is just a quarter circle. This is going to be 1/4 pi r squared in general. We have an r value of 3, so this is 1/4 pi times 3 squared. But again, we're integrating backwards, so that is -1/4 pi times 3 squared. And honestly, I would recommend you leave it like this, because this is numerically equivalent to whatever the answer is. But if you really needed to combine these, we have -9/4 times pi, and then 6, -6, well, let's see here. Actually, I'm just going to leave it like that. I guess you could try to combine these into one fraction, but I mean, we didn't need to simplify this far in the first place, so let's just stop here. Okay, let's move on to g prime of x. So this is the derivative of this function up here. Going from left to right, derivative of 2x is just 2. Derivative of an integral with an x in the upper limit is just plugging x in for t and then applying the chain rule if needed. There's no chain rule to apply really because we just have derivative of x equaling 1. So this is just going to be f of x then. And that is what g prime of x looks like. Okay, now we're actually going to use g prime of x. Now you needed to make sure that you stated g prime of x before using it because they specifically asked for it up here. But now that we've stated it, let's plug -3 in. So that's 2 plus f of -3. And f of -3, that's just the value of -3 on our graph over here. So at -3, our graph takes on a value of 0. This then is just 2 plus 0, which you can simplify if you wish to 2. For part B, we're trying to determine the x-coordinate of the point at which g has an absolute max on the interval from -4 to 3, and justify it. So in order to justify whatever we choose for the x value of our absolute max, we have to show all the different possibilities that could have been absolute maxes. So we need to take a look at the values at the endpoints, -4 and 3, and we also have to look at any critical values. So on this slide, I'm just going to find critical values here. And critical values, that's going to happen when our derivative of 2 plus f of x that we found earlier on, this was g prime, that's going to be 0 at critical values. So we have to solve this. We can solve this by just subtracting 2 from both sides so that we have f of x equals -2. And we are now trying to find the x values where f, this graph here, takes on a y value of -2. So where does that happen? Well, here's the y value, -2. The only place where that intersects the graph of f is right here at this spot. What is this exact x value? Well, we have a slope on this line of, let's see, down 2/1, so -2. Using that line slope of -2, we're going down 2/1 And then we can't go down 2. We need to go down like just 1 here. But if you're only going down 1, that means that you're only going forward 1/2. So this is really the value 2.5, if you're precise about it. And we're now going to use that critical value in just a sec to see if it gives us the absolute max. Now that we've got that one critical value at 2.5, we're going to test that along with the endpoints -4 and 3 in our g function up here. We'll start with the first endpoint. So we've got 2 times -4 plus the integral from 0 to -4. So that's going to come out to -8. And then our shapes that we're doing here, by the way, we're integrating backwards, so we're going to have to subtract some stuff. Our first shape is itself a negative area. We have -1/4 times pi times 1 squared. That's just your first quarter circle. And we have some positive area now. This is 1/4 times pi times 3 squared, which we already looked at before. That's your bigger quarter circle. And again, all of this stuff, all of these two areas that I'm adding together, all has to get negated because we're integrating backwards. Simplifying this a little bit, we've got, let's see, this is -pi/4, and over here we have +9pi/4. That comes out to 8/4 pi, or just 2 pi inside here, but we're subtracting all of that, so this is -8 minus 2 pi. Now, normally, again, I wouldn't simplify this because it's free response and answers don't need to be simplified, but since I have to compare this to other values, I may need to have a better picture of exactly what I'm looking at here. And now that I've done this, I can see that this is a negative number. It's a little bit more negative than -14. All right, let's keep going. We need to do g of 2.5 now. So that's 2 times 2.5 plus integral from 0 to 2.5. So that's going to be 5 plus, well, let's see, if we're going from 0 to 2.5, that's going to be a little bit annoying, but we've got one triangle in there. It's going to be 1/2 times a base of 1.5 times a height of 3. And we've also got a negative triangle that has a base of 1 and a height of 2. So -1/2, 1 times 2. And then what does all this add up to? Again, normally wouldn't simplify it, but we need to get the as close as we can to an exact number on this for comparison purposes. So we've got half of this stuff. Let's see here. Let's start over here. This is the easy part. So this is all going to be -1 over here. Together with this 5 gives us a 4. So it's 4 plus whatever this weird fraction is. Well, half of 3 is 1.5. 1.5 times itself is 2.25. So this is a grand total of, let's see, 6.25. All right. A lot more arithmetic than I want to do without a calculator, but we made it work, right? Now for the last one, we have g of +3. That's going to be 2 times 3 plus the integral from 0 to 3. So we've already kind of figured out what we're doing with this integral, except that instead of having, this first positive triangle minus this triangle, the triangle that's negative now is going to have a base of 1.5 and a height of 3. So pretty much the same as we had over here, but we also have a 6 for that 2 times 3. Now the nice thing about this is that these two triangles have exactly the same area, just opposite signs. So these cancel out, leaving us with just 6. Comparing these, clearly my absolute max happens at 6.25. So that's going to be an absolute max at x equals 2.5. For this next part, we're trying to find all values for which g has a point of inflection and the reason for the answer. Now this one's a little tricky because g prime is not exactly f. It's 2 plus f. But at the very least, we look at the graph of f and we can see that f is changing from increasing to decreasing at x equals 0. Now, if f were just g prime, if g prime were the thing changing from increasing to decreasing at 0, that would tell us that g double prime was changing sign, which would tell us that we had a point of inflection for g. So we need to find a way to kind of connect this to the graph of g prime. Now, g prime is just 2 plus f. So since g prime is really just f shifted up by 2, it's also going to change from increasing to decreasing at x equals 0. G prime is literally just this graph, but it's going to be 2 higher in every respect. So this turnaround spot happens at the same x value. Therefore, based off of this, we can say that G has a point of inflection at x equals 0. For this last problem part, it's really a two-part problem. The first part, they're asking us to find the average rate of change of f on the interval -4 to 3. So let's go ahead and do that. That's going to be f of 3 minus f of -4 all over 3 minus -4. Now we actually have to look at the graph and plug in some values. F of 3 is -3, f of 4 is -1, and then so we're doing essentially -3 plus 1 over 7, which we can reduce if we wanted to -2/7, although that actually wasn't necessary. Now for the next part of the problem, they're telling us there is no point between -4 and 3 for which f prime equals this average rate of change. So they're basically telling us that our a rock does not have a matching I rock somewhere on this interval, which is kind of disappointing because with mean value theorem, we're used to those things kind of matching up somewhere. They're asking us to explain why this statement does not contradict the mean value theorem. So here you have to remember the conditions of the mean value theorem. We need to have continuity on a closed interval and differentiability on the open interval for I rock to match up with the A rock. So let's take a look at those conditions. Continuity, do we have that? Well, they set up here the continuous function f. So yes, we have continuity, and you could look at the graph and see that this is continuous. Do we have differentiability? Well, not really. We have this. We actually have a few trouble spots here. We've got this corner is the most obvious one at x equals 0. And we actually, although I didn't bother putting it in my work, we also, because we have these quarter circles, this actually ends up being a vertical tangent right here. But that one's a little riskier to take a leap of faith on. You've got this corner here. This is kind of the low-hanging fruit. Since we have this corner at x equals 0, that means that our graph is not differentiable on the interval from -4 to from -4 to 3. So therefore, since f is not differentiable on that open interval, that means the MVT does not apply to f on this interval. The MVT guarantees nothing because of this corner.